call them subatomic particles. And you must have also learned in your in ninth standard that the orbit close to the nucleus has less energy compared to the orbit away from the nucleus. Let us first understand what is an orbit. See, orbit is also known as shell. Orbit is also known as shell. Electrons revolve around the nucleus in a specified path. That path is nothing but a orbit. So what is an orbit? Orbit is nothing but the path taken by the electron to revolve around the nucleus is known as an orbit or a shell. And the orbit close to the nucleus has less energy compared to the orbit away from the nucleus. Let us say this is my first orbit. Let us say this is my first orbit. This is my second orbit. And this is my third orbit. Which orbit is very close to the nucleus? The first orbit is very close to the nucleus, so it will have less energy compared to the second orbit because the second orbit is little far from the nucleus. The third orbit, the energy in the third orbit will be a little more than the second orbit because the third orbit is even far compared to the second orbit. Let us now learn about quantum numbers. Each electron in an atom is described by a set of 3 quantum numbers, N, L, M. These numbers are known as quantum numbers. They indicate the probability of finding an electron in space around the nucleus. These quantum numbers, they indicate where the electrons can be found around the nucleus. Let us first learn about principal quantum number. Principal quantum number is used to denote the orbits. That's my first orbit. This yellow color line or the orange color line is my second orbit. This is my third orbit. Principal quantum number is used to denote the orbits. We say that principal quantum number gives the size and energy of the main shell. Shell is nothing but orbit. Why do we say that principal quantum number is related to the size and energy? Obviously, if the value of n increases, the size and energy also increases. Why and how? See, that's my first orbit, the blue one. When I write n is equal to 1, it pretty much means that this is the first orbit. Orbits are denoted by principal quantum number lowercase n. When I write n is equal to 2 here, it means that this is my second orbit. The golden color circle, this is my second orbit. And again, this is my third orbit. So you see, as the n value increases, the n value is increasing from 1 to 2, from 2 to 3. As the n value increases, the size also increases. When n is equal to 1, the size was this much. When n is equal to 2, the size is this much. When n is equal to 3, the size is this much. So the size of the atom is increasing as the n value increases. And we say that the energy also increases, right? Because energy of second orbit is more than the first orbit. Energy of third orbit is more than the second orbit. What is a radius in general? A radius is the distance from the center of the circle to a point on the circle, right? In the same way, what is atomic radius here? Atomic radius is the distance from the center of the nucleus to the outermost orbit. That is known as atomic radius. So as the value of n increases, as the principal quantum number increases, the atomic radius also increases. If the atomic radius increases, it obviously means that the atomic size is also increasing, right? As the atomic size increases, the energy obviously increases because electrons will move further away from the nucleus, so they will have more energy. And these shells here, shell is nothing but an orbit, so these shells here are denoted by the letters K, L, M, so on. N is equal to 1 means the first orbit denoted by K. N is equal to 2, the second orbit denoted by L. N is equal to 3, the third orbit denoted by M, so on. You can see that in this table also. N, 1, 2, 3, 4, K, L, M, N. The first orbit denoted by K, second orbit denoted by L, so on, right? And now we'll learn about angular momentum quantum number. Angular momentum quantum number is denoted by lowercase l, and it takes values from 0 to n minus 1. Each L value represents a subshell. Each value of L is related to the shape of a particular subshell in space around the nucleus. If L value is 0, name of the subshell is S. L is equal to 1 means P subshell. L is equal to 2 means D subshell. L is equal to 3 means F subshell. Let us say the value of n is 1. When the value of n is 1, L can have how many values? L can have only 0 because L takes values from 0 to n minus 1. N itself is 1, 1 minus 1 is 0, so L value would only be 0 here. When n is equal to 1, there is only one subshell. When n is equal to 1, there is only one subshell. L is equal to S. And we denote it by 1s. See, this is pretty simple. Why do we denote it like this? Orbitals are denoted like this. NL. This N is our principal quantum number. This L right here is the angular momentum quantum number. The value of N is 1. So in place of N, I'm going to write 1. And what is the value of L here? L is 0. 0 means it is S subshell. So I'll write S, 1s. So this is designated as 1s orbital. In the same way, when n is equal to 2, what are the values of L? L, we know that it takes values from 0 to n minus 1. So 0 to n minus 1. What is n? 2. 2 minus 1 is what? 1. So L takes values from 0 to 1, which means L takes these two values. How do we represent it in this form here? Simple. N value is 2. So here in place of n, I'm going to write 2. Next, L. L is 0. 0 means it is S orbital. So I'm going to write S here. So when n is equal to 2, n is equal to 2 means the second orbit. The second orbit or the second shell. Second shell has two subshells. Second shell has two subshells. 2s and 2p. Again, see here, n is equal to 2. So n, I'm writing 2 here. L value is 1. 1 means p orbital. So I'm going to write p. N 2p. Right. So when n is equal to 1, we have one subshell. We had one subshell. When n is equal to 2, we had two subshells. 2s and 2p. These are two subshells. Let us consider n is equal to 4. What are the possible values of L now? L takes values from 0 to n minus 1. Right. What is n here? 4. 4 minus 1 should be 3. So L value should be 0, 1, 2, 3 up to 3. 0, 1, 2, 3. How do we write it? 4. First I'm going to write n value, right? N value is 4. So 4 I have written. And then I have to write n L here. L value is 0. 0 means it is S orbital. So 4s. In the same way, 4. 1 means P. 4p. 4. 2 means D. 4d. 3. 3 means F. 4f. So in the fourth orbit is also known as shell. So in the fourth shell, we have 4 subshells. This stuff is pretty easy. If in first shell, you have one subshell. In second shell, you have two subshells. Likewise, in third shell, you will have 3 subshells. In fourth shell, you have 4 subshells. What is magnetic quantum number? Magnetic quantum number is denoted by M subscript L. So M subscript L is magnetic quantum number, and magnetic quantum number, it gives us, it talks about the number of orbitals each subshell has. It talks about the number of orbitals each subshell will have. Now, I told you that subshells are denoted by S, P, D, F. And what are the L values for these subshells? Let's just write down 0, 1, 2, 3, so on. L value is 0, means it is S subshell. If L value is 1, it is P subshell. If L value is 2, it is D subshell. If L value is 3, it is F subshell. Now, let us substitute L as 0. L as 0. 0 means it is S subshell, right? So let me substitute L as 0. 2 I'm writing as it is. In place of L I'm substituting 0. 2 into 0 is 0. 0 plus 1 is how much? 1. So how many orbitals S subshell has? It has 1 orbital. So S here, S has 1 orbital. In the same way, let us substitute the value of L as 1. 1 means it is P subshell, right? Let us substitute the value of L as 1. 2 ones are 2, 2 plus 1 is 3. So how many orbitals are there in P subshell? There are a set of 3 orbitals in P subshell. How many orbitals will be there in D subshell? Obviously, the L value of D is 2. So in place of L, I'm going to substitute 2. 2 into 2 is 4. 4 plus 1 is how much? 5. Which means D will have how many orbitals? D will have 5 orbitals. The value of L is 3 here. Let us substitute the value of L as 3. 2 into 3 is 6. 6 plus 1 is how much? 7. So F has how many orbitals? F has 7 orbitals. And you can see the shapes here. S has only 1 orbital. And the shape of S orbital is spherical in shape. P has 3 orbitals. Px, Py, Pz. 3 orbitals. D it has 5 orbitals. 1, see here, D, Yz, D, Xz, D, Xy, D, X square minus Y square, D, Z square. These are 5 orbitals that you have in D subshell. So D subshell has 5 orbitals. 1, 2, 3, 4, 5. P subshell has 3 orbitals. Px, Py, Pz. S, S has only 1 orbital. So magnetic quantum number talks about the number of orbitals that are available in each subshell. And what are the values that magnetic quantum number takes? Magnetic quantum number takes values from minus L to plus L. Magnetic quantum numbers takes values from minus L to plus L. For S orbital, the value of L is 0. So what are the values that M should take? M should take values from minus 0 to plus 0. There's no such thing. 0 does not take any negative sign, positive sign. So the value of M here is 0. If the value of L is P, then what are the values of M? M can take values from minus 1 to plus 1, right? So M will have how many values? 3 values. So P orbitals, P subshell, it's split into 3 orbitals. In the same way, if L value is 2, what are the values here of M? M can take values from minus 2 to plus 2, right? M will take values from minus 2 to plus 2. How many values? 1, 2, 3, 4, 5. So D subshell, it splits into 5 orbitals. And what are the names of D orbitals? DYZ, DXZ, DXY, DX square minus Y square, DZ square. Let us now try to understand this table right here. N is equal to 1. N represents the orbit or the shell. The first orbit, it will have only one subshell, right? N represents the orbit. Orbit is also known as shell, right? So the first shell will have only one subshell. The second shell will have 2 subshells. The third shell will have 3 subshells. 1, 2, 3, 3 subshells. The fourth shell will have 4 subshells, right? And what are the possible M values? M takes values from minus L to plus L, right? M takes values from minus L to plus L. So L value is 0, which means M will take values from minus 0 to plus 0. There's no such thing. 0 will not have a sign. So only number that is, so the only value for M is 0 here. When the value of L is 0, M value will be 0. And when the value of L is 1, obviously M value would be minus 1 to plus 1, right? Again, when the value of L is 2, M value will be from minus 2 to plus 2. When the value of L is 3, M will take values from -3 to +3. Now n is equal to 1. Here this row, let us only read this row, the very first row. Let us only read the very first row, which is white in color. N is equal to 1 here. L is 0. So what is the subshell notation? Subshell notation will be 1s. Why? Come on, subshell notation will be 1s because we denote the subshell by this NL. This n is our principal quantum number. This L is our angular momentum quantum number, which is used to denote the subshell. The value of n is 1. So in place of n, I'm going to write 1. The value of L is 0. 0 means it is S subshell, right? So this will be 1s. If you forgot already, write it once again. SPDF, value of L for S is 0. The value of L for P is 1, D is 2, F is 3. Just write it down like this: L 0, 1, 2, 3. In the same way, N value is 2. So in place of N, I'll be writing 2 here. L value is 0. 0 means it is S subshell. So 2s. When the value of N is 2 and the value of L is 0, what is the subshell notation that we have? And when the value of M is 0, the subshell notation is 2s. N value is 2. L value is 1 here. What would be the notation? Simple. N value is 2. L value is 1. 1 means P subshell. So the notation would be 2p. And how many orbitals are there in P subshell? There are 3 orbitals. We have already seen P subshell is divided into 3 orbitals: px, py, pz. So P has how many orbitals here? P subshell has 3 orbitals. S subshell will have only 1 orbital, right? S subshell has only 1 orbital. P splits into 3 orbitals: px, py, pz. So P has how many orbitals? 3 orbitals. D is splitting into 1, 2, 3, 4, 5 orbitals. So D is splitting into how many orbitals? 5 orbitals. F, likewise, F is splitting into 7 orbitals. We have seen this already. F has how many orbitals here? 7 orbitals. So F has 7 orbitals. And what are the maximum number of electrons in each subshell? See, S has 1 orbital. Remember, the number of electrons that each orbital can occupy, the maximum number of electrons that each orbital can occupy is 2. How many electrons can each orbital occupy? It can occupy a maximum of 2 electrons. So S orbital, it has only one. S subshell has only 1 orbital. So this 1 orbital can have a maximum of 2 electrons. P subshell can have a maximum of, P subshell has 3 orbitals, right? 3 orbitals: px, py, pz. So this orbital will have 2 electrons. This orbital can have maximum of 2 electrons. This orbital can have a maximum of 2 electrons. So altogether, how many electrons will be there? 6 electrons. D subshell, it has 5 orbitals: dxy, dyz, dxz, dx square minus y square, dz square. And each orbital will have a maximum of 2 electrons. Each orbital will have a maximum of 2 electrons. 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 2 is 10. So D will have a maximum of 10 electrons. F, it is splitting into 7 orbitals. Each orbital will have 2 electrons. So 2 into 7 is 14. So this will have 14 electrons. Important. This is very important. This you have to know it. If you don't know this thing, it is almost impossible for you to write down the electronic configuration. What is spin quantum number? See, electrons can have a spin, a clockwise spin, and electrons can have an anti-clockwise spin. If the electrons spin clockwise, we say that the spin is plus half. And when the electrons spin anti-clockwise, we say that the electrons have minus half spin. And remember, in each orbital, orbital, if one of the electron has a positive spin, the other electron will have a negative spin. So there can be a maximum of 2 electrons only in a orbital. This will be a little more clear when we write down the electronic configuration. What is electronic configuration? The distribution of electrons in shells, subshells and orbital in an atom is known as electronic configuration. You already know what is a shell, right? Shell is nothing but a orbit. Subshell, we know that subshells are denoted by S, P, D, F, right? And what is an orbital? P has 3 orbitals, Px, Py, Pz. So these are nothing but orbitals. Let me be a little more clear with the shells, subshells and the orbital. I believe I can explain it to you this way. See, an orbit is also known as a main shell. Orbit is also known as a main shell, and we have seen how many subshells can each shell has. The first shell can have only one subshell, the second shell can have 2 subshells, the third shell can have 3 subshells, the fourth shell can have 4 subshells. We have already seen this earlier, right? Let me go back and see here. The fourth shell can have how many subshells? 4 subshells. The second shell can have 2 subshells. We have already seen this, right? And in turn, these subshells are splitting into orbitals. Like P subshell is splitting into 3 orbitals. So these are orbitals. So I hope you now know the difference between shell, subshell and orbital. Right, and each orbital can have a maximum of how many electrons? 2 electrons. Can you tell me how many electrons will be there in every shell? Let me ask you, how many electrons are there in second shell? How many electrons are there in second shell? To find out the number of electrons, we have a pretty simple formula, 2n square. So in place of n, substitute 2 here. 2 square is how much? 4. 2 4s are 8. Which means the second shell will have 8 electrons. When I say shell, I'm referring to the orbit. A orbit is nothing but the path taken by the electrons to revolve around the nucleus, right? So the second orbit or the second shell has a maximum of, will have 8 electrons. Before we start writing the electronic configuration, let us go through the Pauli's exclusion principle. Pauli's exclusion principle states that no 2 electrons will have all the 4 quantum numbers same. To understand this, let us consider helium atom. The atomic number of helium is 2. Atomic number is 2. It means it has 2 electrons. It has 2 electrons, and both the electrons are there in the first orbit. Both the electrons are in the first orbit. Why? Because the first orbit can have a maximum of 2 electrons, right? Let's say in place of n, I substitute 1 here. In place of n, I am substituting 1 here. What does it mean? 1 square is 1, 2 ones are 2. So the first orbit can have 2 electrons, right? So both of the electrons here will occupy the first orbit, because the first orbit can have 2 electrons. So both the electrons will enter into first orbit. And what is the L value? The L can take values from 0 to n minus 1, right? 0 to, what is the value of n here? 1. 0 to 1 minus 1. 1 minus 1 is 0. So when in the first shell, you have only one subshell. In the first shell, you have only one subshell. So both the electrons will have the same n value. Both the electrons will have the same L value. And what about magnetic quantum number? What about magnetic quantum number? Magnetic quantum number takes values from minus L to plus L, right? Magnetic quantum numbers takes values from minus L to plus L. What is L here? 0. So minus 0 to plus 0 is nothing but 0. So both the electrons have the same n value, have the same L value, they have the same magnetic quantum number value. But what about the spin? We know that if the first electron has a spin of plus half, the second electron will have obviously a spin of minus half, because they will have opposite spins. So Pauli's exclusion principle says that no 2 electrons will have all the 4 quantum numbers same. For an example, helium atom. In helium atom, we see that there are two electrons. Both of them have the same principal quantum number, same value of principal quantum number, same value of azimuthal quantum number, same value of magnetic quantum number, but the spin quantum number, it changes. They don't have the same spin quantum number value. So Pauli's exclusion principle here is a bit straightforward. It says that no two electrons will have all the four quantum numbers same. No two electrons can have all the four quantum numbers same. What is Aufbau principle? Aufbau principle says that the electrons are assigned to orbitals in order of increasing value of n plus L. Don't get confused here. Increasing value of n plus L. How to find out the value of n plus L? This is pretty easy. Let us say I want to find out the n plus L value of 2p. 2p. See here. This 2 means the value of n is 2. Let us find out the n plus L value here. For 2p, what is the n value? N value is 2. Plus, what is the L value? Go up and see here. The value of L is 1. So n plus L value is 3. For 2p, the n plus L value is 3. And let us consider 2s here. For 2s, what is the n plus L value? N value is 2. S, what is the S value? S value is 0. 2 plus 0 is 2. So which has a lower n plus L value? 2s or 2p? The n plus L value of 2s is 2. N plus L value of 2p is 3. 2 is lesser or 3 is lesser? Obviously 2 is less than 3, which means 2s has a lesser n plus L value. So electron will first occupy 2s because it has a lesser n plus L value, and then it will occupy 2p. Electrons will occupy orbitals which have a less n plus L value. At times what really happens is n plus L values become equal. N plus L value becomes equal. During those cases, electron will occupy the orbital which has lower n value. Let us say I have 4p and 3d. I have 4p and 3d. I want to find out the n plus L value of 3d and 4p. Finding out n plus L value is not at all difficult. This 3 that you see here, this is the n value, because we see that the orbitals are denoted like this, right? N, L, X. This thing right here is nothing but the n value. This thing is nothing but the n value. So n value is 3. N value is 3. Plus, what is the L value? What is the L value? We have D here. We know that D value should be 2. So value of L value for D is 2. 3 plus 2 is 5. Let us do the same thing for this also. N value is 4 here. N value is 4. L value for P is 1. So 4 plus 1 is 5. L value for P is 1. So 4 plus 1 is 5. Both of them in this case, they have the same n plus L value. Both of them have the same n plus L value. But which has a lower n value? 3d has a lower n value. That is the reason the electron will first occupy 3d orbital and then it will occupy 4p orbital. So this Aufbau principle is pretty easy. It says that the electrons will occupy the orbital which has a lower n plus L value. In case both the n plus L value are equal, then it will occupy the orbital which has lesser n value. As simple as that. This colorful diagram that you see out here is known as Euler's diagram. Euler's diagram helps us in writing down the electronic configuration. It helps us in writing down the electronic configuration. Let me draw this Euler's diagram for you. It is pretty simple. What you have to do is first write down 1 time, write down 2 times, 3 times, 4 times, 5 4 times, and then keep decreasing. 6 3 times, 7 2 times, 8 1 time. So what I'm doing here, I'm writing 1 time, 2 times, 3 times, 4 times, 4 times and then decreasing it, 3 times, 2 times, 1 time. 1 S, S, P. Subshells are denoted by S, P, D, F, right? So write down here S, P, S, P, D, S, P, D, F, S, P, D, F, S, P, D, S, P, S. That's it. So drawing a Euler's diagram is simple. Electrons, you see the direction here, the pointer it is here, and then the pointer is here, then the pointer is here. This is showing in what sequence the electrons will enter the orbitals. The sequence is simple. First, electrons will enter into 1s orbital. After 1s orbital is completely occupied, the electrons will go into 2s orbital. Once 2s is completely filled, they go into 2p orbital. If 2p is filled, they go into 3s orbital. When 3s is filled, they go into 3p orbital, then 4s, then 3d, then 4p, and so on. Using this Euler's diagram, let us write down the electronic configuration. See, electronic configuration is pretty simple. Let us say I have magnesium. The atomic number of magnesium is 12, which means that it has 12 electrons. The first 2 electrons will go into 1s orbital. We know that S can have a maximum of 2 electrons because S has only one orbital. Each orbital can have a maximum of 2 electrons. P subshell, we know that P splits into 3, right? 3 orbitals, Px, Py, Pz, and each orbital can have a maximum of 2 electrons. So 2, 2, 2, 6 electrons. P can have a maximum of 6 electrons. And we know that D has a maximum of 10 electrons. Why? Because D splits into 5 orbitals, right? D has a total of 5 orbitals, dxy, dyz, dxz, dx square minus y square, dz square. And in each orbital can have a maximum of 2 electrons, 2, 4, 6, 8, 10. So D can have a maximum of 10 electrons. Remember this thing? Writing down the electronic configuration will be a cakewalk for you. So magnesium, atomic number of magnesium is 12, which means it has 12 electrons. The first 2 electrons will go into 1s orbital. After that, 2 more electrons will go into 2s orbital because S can have a maximum of 2 electrons, right? So 2 electrons will enter into 2s orbital. Then 2p. How many electrons can be there in p orbital? 6. So 6 electrons will go into 2p orbital. After 2p, they are going into 3s orbital. S can have a maximum of 2 electrons, right? So 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12. So all the 12 electrons got occupied. So this is the electronic configuration for magnesium. 1s2, 2s2, 2p6, 3s2. That's the electronic configuration for magnesium. Let me write down the electronic configuration for chromium. Chromium has an atomic number 24. What should be the electronic configuration? The first 2 electrons should go into 1s. After 1s is completely filled, the rest of the electrons, they go into 2s. After 2s, electrons will go into 2p. How many electrons can p subshell occupy? 6. So 2p 6. After 2p, they are going in, the rest of the electrons will go into 3s. S can occupy a maximum of 2 electrons. So in 3s you will have 2 electrons. After 3s you have 3p. P again can have a maximum of 6 electrons. So 3p will have 6 electrons. After 3p you have 4s. 4s. S can have a maximum of 2 electrons. So 4s will have 2 electrons. After 4s, electrons go into 3d orbital. D can have a maximum of 10 electrons. But how many electrons are remaining now? 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 18 plus 2, 20. 20 orbitals, 20 electrons are already occupied. So only 4 electrons are remaining. So 4 electrons will go into 3d orbital. Let me now write down the electronic configuration for zinc. The atomic number for zinc is 29. 1s. S can have 2 electrons. After 1s it goes into 2s. S can have 2 electrons. After 2s it goes into 2p. P can have 6 electrons. After 2p it goes into 3s. S can have 2 electrons. After 3s it goes into 3p. P can have 6 electrons. After 3p it goes into 4s. S can have 4 electrons. After 4s it goes into 3d. D can have 10 electrons. But let us first count how many electrons are left out. 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 is 18, 18 plus 2 is 20. So 20 electrons have already occupied the orbitals. 29 minus 20 is 9, so 9 electrons are remaining. So the rest of the 9 electrons will enter 3d orbital. So this is how you write down the electronic configuration. Chromium and zinc, you have written the electronic configuration, which is well and good, but the electronic configuration of chromium and zinc is a little different than this. Why? Because just to gain stability, d orbital will take 1 electron from 4s orbital. The 3d orbital will take 1 electron from 4s orbital, and it becomes 4 will become 5. This 2 becomes 1. This 4 will become 5. And in order to gain stability again, 3d orbital takes 1 electron from 4s, and this 9 will become 10. Completely filled orbitals and half filled orbitals are more stable. D can have a maximum of 10 electrons. So if D has 10 electrons, it is completely filled. Half of 10 is what? 5. So if D has half filled electrons, it is stable. Or if D has completely filled electrons, it is stable. That's the reason there is a little change in the electronic configuration of chromium and zinc. Lastly, we will go through Hund's rule. Hund's rule is not at all difficult. See, let us consider carbon. Atomic number of carbon is 6, which means it has 6 electrons. The first 2 electrons will go into 1s orbital. After that, 2 electrons will go into 2s orbital. After 2s, the rest of the electrons will go into 2p orbital, right? So the first 2 electrons go into 1s, the next 2 electrons goes into 2s. The rest of the 2 electrons, remaining 2 electrons, they go into 2p orbital. Let me write this down in a box form. 1s, it has 2 electrons. 1, 2, it has 2 electrons. 2s, it also has 2 electrons. 1, 2, 2 electrons. P, we know that P splits into 3 orbitals, 2px, 2py, 2pz. P subshell, it splits into 3 orbitals, 2px, 2py, 2pz. Right? How many electrons are there in P subshell? 2 electrons. The first electron can go into any one of these orbitals. Let us say the first electron goes into 2px orbital. The second electron cannot get paired here. It goes into 2py or 2pz. Why? Why? Because these are known as degenerate orbitals. Orbitals which have same energy. Orbitals which have same energy, almost same energy. Orbitals which have almost same energy are known as degenerate orbitals. So in degenerate orbitals, what really happens is electron pairing will not take place until and unless all the degenerate orbitals are occupied by 1 electron each. So Hund's rule states that electron pairing takes place only after all degenerate orbitals are occupied by 1 electron each. So if in case I have one more electron, that electron will not get paired here because these are degenerate orbitals. Pairing cannot happen until and unless all the orbitals have 1 electron each. So if I have another electron, it will go here in 2pz, but it will not get paired with 2px or 2py. If now I have one more electron, then only it will get paired. So in degenerate orbitals, pairing will take place only after all degenerate orbitals are occupied by 1 electron each. I hope you understood. In case you have any questions, any doubts whatsoever, feel free to interact with me by logging on to our website and using the chat tool on our website. Thank you so much for watching. I'll see you all in the next video. Have a very nice day. Goodbye.